Hola, ¿qué tal? ¿Todo el mundo bien? Hoy vamos a hablar de yerba y mate. Oh, I'm sorry. This is my English channel. Sorry. Yeah, on the end of this week, I'll be starting my Spanish channel up. I'm going to start it up. And so for those of you who are interested, well, I'm going to be putting the link in the description. Want to remind everyone that I do have a book out. We uploaded, I think, a couple weeks, 10 days ago now. The Rope Hypothesis tells you a little bit about the new vision of the universe, how it works. And you can download that book at ropehypothesis.com. It's free, illustrated. Okay, if you can translate it to some language, your native language, well, please contact us at tokakaka@hotmail.com. Okay, we'll be glad to send you a file that you can modify, and if you translate it, send it back. We'll upload it for you. Okay, and put your name in lights, and we thank you in advance. Okay. Well, what am I going to talk about today? I'm going to talk about time. What is time? The mathematicians say it's the fourth dimension. Okay, so we have time, the fourth dimension. Where did they get this? Okay, someone had a bad dream, a nightmare or something? Well, let's go a little bit through it. Let's see if we can get to the bottom of it to some degree, okay? See if we can figure out how they came up with this notion that time is a dimension. It wasn't always, by the way, okay? Time's been a dimension only for the last maybe 100 years, more or less, okay? Before that, time was not a dimension. And that's what I want to look at, that little history, okay, today. Okay, so we start with, as usual, with the Greeks, because that's where we inherited a lot of our notions of geometry. And I'd say all of them, really, because that's the foundation of mathematics, started in Greece. Okay, so we have to give credit to the Greeks for this, no doubt about it. And we had on one hand, like I said the other day, Mr. Aristotle, okay, and he was interested in what we could call physics, science. He was interested in explaining how this universe works, okay, and so he applied points and lines to things such as location, distance traveled, motion, time. Okay, he also used number. Okay, and that contrasted with a fellow who came one or two generations later. We don't know when Euclid was born. Okay, or when he died, but Euclid wrote a book called Elements. In it, he synthesized the notions the Greeks had of geometry, specifically as a foundation for mathematics. Okay, so he used point, line, plane, etc., but he used them for geometry, whereas Aristotle used them for to try to figure out I guess you could say, the foundations of physics. That's why his book is called Physics. Okay, so that's our starting point. So we're not going to be interested in Euclid right now. We're going to be interested in Aristotle, because the notion that time is a dimension has little really to do with geometry. It has to do with trying to explain gravity, warpage of space-time, four-dimensional space-time. It has to do with a lot of that, and that the starting point is Aristotle, absolutely not Euclid. Okay, so let's go with Mr. Airy here, and the first notion he tries to stepping stone, you could say the first cornerstone, is the notion of what motion is. Okay, and he's going to start by using the word line to simulate motion. Okay, so he says locomotion in a regular path, example in a circle or on a straight line. So you're going to see that word line constantly related to locomotion, motion. Okay, a motion cannot be regular if its path is an irregular magnitude. Example, a broken line. Okay, spiral or other magnitude. Again, he uses magnitude to talk about motion. Okay, and he relates magnitude to line. He says, or any other magnitude. So they're not thinking of line as a geometric figure. They're thinking of line as a magnitude, some number on a number line. What else can you call it? Okay. Distant in a straight line, okay, for the shortest line is definitely limited, and that which is definitely limited constitutes a measure. Talking about measuring now, okay, measuring numbers. We're talking about a number line. That's what the line means to them. They're not going to use, at least Aristotle, he's not going to use the line to talk about geometry. He's going to use the line as it is used today by relativists and mechanics, quantum mechanics, okay? And they're going to use it in lieu to pictorially depict motion. That's essentially where these guys are at, okay? A thing is in succession when it is after the beginning in position or in form, and when further there is nothing of the same kind as itself between it and that to which it is in succession. Example, a line, a unit. When he talks about unit, he's talking about numbers, he's talking about dots, points. That's what he means when he talks about unit. Okay, so you can see he's going to use the point, the line, and he's going to talk about position or location, place as he called it, and he's going to be talking about motion and time. Okay, this is where he's headed. Okay, and yeah, the first thing he has to define is continuous. What does he mean by this adjective he calls continuous? And here we have a major discrepancy between physics, rational physics, and what all of mathematics means by continuous, okay? So mathematical physicists, they follow Aristotle. Rational people don't, okay? So let's make sure that you understand that. So what did Aristotle say for continuous? He says, no continuous thing is divisible into things without parts. In other words, according to Aristotle, something that is continuous is segmented, made of parts, of discrete points. Okay? If it is divisible, it must be divisible either into indivisibles or into divisibles that are infinitely divisible, in which case it is continuous. Okay? So these are essentially different ways of saying the same thing. Neither a line nor a surface, nor surface also, meaning planes, right? Nor in fact anything continuous can be indivisible. Everything has to be divisible if it wants to be continuous, okay? And lines may be infinitely divided. Well, you see there the two notions that we have, one from Aristotle, the other one from rational physics. And according to rational physics, continuous means made of a single piece. Aristotle and his mathematicians, all the people that followed him, they think of continuous as something which can be broken up into pieces. And so the question comes up whether, if you have all these dots, pieces, squares, whatever you want to call them, all these little pieces that form this continuous structure, how is one little piece separated from the next one? Obviously, you got a bump because you got to jump a divide. That's some kind of space that divides these constituents. You can't avoid it, okay? And here I'll give you an example. Here's a Rubik's Cube, okay? Imagine that's a square, okay? And it's made out of squares. Well, those black lines that divide each one of these squares, or even for the cube, okay? You know, you got to jump over that line to get to the other square. And so no matter how you look at it, if a square or a cube is made out of parts, right, each part is separate from the next one down, then it cannot be continuous according to what a rational human would call continuous. Now, obviously, only if it's made out of a single piece is something continuous. And we can use that notion to talk about something that is continuous in an ideal frame, okay? Frame of mind, frame of discussion. But you cannot use the concept that Aristotle has and all the mathematicians have for what they think is continuous, which is something something made of pieces, okay, segmented. Here's an example. Okay, here is this continuous. Here you have a triangle, and it's made out of all these little points. Would you think that that's continuous? Is that a smooth surface? And here, you compare it against this. Okay, how's that? So something that is continuous is made of a single piece and not made of points, as the mathematicians or Aristotle would have you believe. Okay, so this is the issue. The issue is he starts off on the wrong foot, because he's going to be talking about motion. And he's going to build motion with locations. And a location is a point, a dot. That's what he's going to depict it with, right? That's his pictorial representation of a location, of a position, of a place, as he called it. He's going to use the unit, or he's going to use the dot, the point, to represent it. And of course, if one point is separated from another point, well, then you don't have continuity. Except according to him, because he says between any 2 points you'll find another point, or you'll find a line, and the line is made of points. So it's infinitely divisible. So this is the notion that we have a problem with. It's conceptually wrong, conceptually irrational with what a rational human being understands by continuity. Okay, and again, you can dispute that if you want, and I don't want you disputing it from a mathematical point of view. You need to challenge it from a physical point of view. What do you mean by continuous? Okay, and of course, in ordinary days, nothing is continuous. Everything is discrete, except under the rope model, the original thread, the lonely thread that forms all of matter. That's the only thing we say is continuous, made of a single piece, okay? But you'll have to go to the book to find out what that's about. So what does Arya do next? Well, he defines or identifies three types of motion, okay? And here they are. This comes from his book 5. One thing causes motion accidentally. Another partially because something belonging to it causes motion. Okay? Another of itself directly. That which directly causes motion, that which is in motion, and that in which motion takes place, namely time. Now he introduces time there. Okay? And that from which and that to which it proceeds. Okay? And he adds, he says, for every motion proceeds from something and to something, that which is directly in motion being distinct from that to which it is in motion towards, right? And that from which it is in motion. So he's talking running away, going to something, approaching something, okay? He's talking about the object itself doing the motion. And he does give some examples, okay? Here's one of the examples that he gives, or a couple of the examples. He says, take the three things, wood, hot, and cold, okay? He calls them things, hot and cold. They're concepts, but he calls them things. Again, another evidence you could say that he doesn't define the word object. He doesn't tell you what a thing is, okay? Or he doesn't identify that. And he says the first is that which is in motion. The second is that to which the motion proceeds. And the third is that from which it proceeds. Okay, motion is in the wood, not in its form, for the motion is neither caused nor experienced by the form or the place or the quantity. So we are left with a mover, a moved, and a goal of motion. I do not include the starting point of motion, for it is the goal rather than the starting point of motion that gives its name to a particular process of change. Thus, perishing is changed to not being, and becoming is changed to being. That more or less is his notion of existence or coming into existence. That's what he's talking about, okay? So he makes sure you understand that one of the problems we have today, if you look up the word motion or movement, and it'll say a change in position or whatever, change in place or whatever nonsense that ordinary dictionary has, which is what the mathematicians have. And it turns out that Aristotle specifically stated that motion and change are two different words. They're not synonyms, okay? And so he says that here in his book, okay? He says, movement is change from one form to another, whereas change implies a pair of opposites, alteration. If you go from hot to cold, you changed. It's a type of motion, but it's not exactly the same thing as change, okay? Because motion is actually change in form, whereas change requires that you go to your opposite. You have to turn black into white or on into off, that sort of thing. That's what he was referring to, okay? And of course, he goes from there to time, okay? Jumps over because now he's got two foundations. He's got continuity on the one hand, and on the other one he's got motion. He's got a notion of motion, okay? And so he moves on to time. He says the science of nature is concerned with spatial magnitudes and motion and time. He's talking about physics, okay? He's going to set like the foundations of physics here. And each of these, at least, is necessarily infinite or finite. This concerned him a lot, whether something is finite or infinite. I guess the Greeks dealt a lot with this issue, infinity, right? And that's why they got into numbers. They realized they could count forever conceptually. So they got into this notion of infinity, and they always related it to numbers. You can't introduce infinity unless you've got mathematics. In other words, you've got arithmetic. You need the number line. You need those numbers to go off into nowhere land. Wherever infinity is, that's where you'll find the last number. So go and find it, right? Hence, it is incumbent on the person who specializes in physics to discuss the infinite and to inquire whether there is such a thing or not, and if there is, what it is. No, in physics, no. Maybe in mathematics. In physics, we care not one iota about infinity, okay? But that was his notion, and that's the notion the mathematicians have today, mathematical physicists, they call themselves. Belief in the existence of the infinite comes mainly from 5 considerations. And the first one, I'm not going to mention the others, from the nature of time, for it is infinite. Already, Ari is telling us that time is infinite. Why? Because time, well, we're going to find out what time is in a second here, but he's saying it's infinite. And obviously, like I said a minute ago, it's something related to numbers or the number line, because the number lines or the number of numbers is infinite, okay? You can count until you die if you want, and beyond. Even when you go to heaven, you can continue counting, okay? Does time belong to the class of things that exist or to that of things that do not exist? He asks this question, does time exist? And this is a valid question. Does time exist? And for that, we need to define the word exist, which Mr. Ari and no one since then has ever defined. Okay, now we define it in rational physics and rational science. We define the word exist, so now we can use it consistently, okay? And in order for something to exist, the first thing it's got to be is a thing. It's got to be a something. It's got to be an object, a medium, a substance. It's got to have shape. If it doesn't have shape, you can't apply the word exist to it. You cannot say love exists, intelligence exists, information exists. You cannot say that, not in physics, not in science. You can say that in ordinary speech, and that's where people get confused because they want to extrapolate the notions we have in ordinary speech directly into science, indiscriminately. You can't do that. In physics, or in science in general, you have to define the term first. Then you can use it to qualify whatever you want, okay? And so we define the word exist as an object that has location, okay? So it's got to be an object, and it's not sufficient. It's got to also have location. If God wants to exist, he's got to be an object first. He's got to have shape, and then he's got to have location. Otherwise, poor old God does not exist. Sorry. And if God has shape, but he's only in your brain, and you see an old man there in your eye, well, he still doesn't exist. He has no location. Your thoughts don't have location. Your brain does, and every atom in there, but not God. Okay. Okay. So yeah, we have a problem because he hasn't defined. Aristotle hasn't defined what he means by exist, and he asks a valid question: does time exist? And a lot of people say, well, yeah, time exists, time is real. But they're using this notion of ordinary speech, which they automatically bring into their dissertation. You can't do that. You got to define the word exist before you can use it in science. It's a very important word, so important that that we define physics as the science of existence. Physics tries to elucidate what exists out there. Physics only deals with what exists. Okay, it does not deal with what does not exist. Okay, so where do we go from here? Well, he defines time finally. Okay, here it is, the definition. Okay, so what does Ari say? He says that time is number of movement, quantity of movement, interval of movement. He's referring to some kind of number that he's going to apply to, he's going to talk about seconds essentially, or minutes, or whatever measure they had in those days. Number of movement in respect of the before and after. Okay, before and after have to do with time, but with qualitative time. Okay, it's qualitative. Whereas he's talking about number, which is quantitative. See, when you say yesterday, today, tomorrow, you're talking about qualitative time. Okay, those are before and after. You know, all that is qualitative. The notions we have of time, but from a qualitative standpoint. And that's the only thing that you can bring into physics if it serves any purpose. I don't think it does in any sense, but maybe there is. I can't say that it doesn't. We don't use time. And when I say we don't use time, specifically I'm referring to the fact that we do not use numbers. We do not use seconds, minutes, years, whatever, because we cannot explain anything with those numbers, with those units. Okay, that's the issue. Time is a measure of motion and of being moved. Okay, so he's talking about measure of motion. That's what he's referring to. Time is number, the now and the before. Time is not motion, but number of motion. And what is at rest also can be in the number of motion. Okay, I don't know what he meant by rest, because as far as I know, no atom in the universe is at rest. At rest with respect to what? You know, you can be at rest, you can be standing totally still, and you're moving with respect to Jupiter because Jupiter is moving. So your distance with respect to Jupiter is changing simply because the Earth rotates around the sun, Jupiter rotates around the sun, and everything in the universe is rotating around something. So there is no such thing as rest. But that's going to be important because the relativists invented the so-called frame of reference. They put a stake on the ground, put a corner there, and they say, well, with respect to that corner, you're not moving. They had to stop the universe in order to make their case mathematically. Okay, keep that in mind. Rest is very important. They don't call it rest. They do talk about rest mass, for example, and that sort of thing. But they're going to talk about frame of reference. Okay, and that's putting a stake in the ground. Time is not motion, but number of motion. And what is it? Okay, I already said that. Can be in the number of motion. The now is an end and a beginning of time. So time is always at a beginning, at an end. Okay. So these are the notions that good old Ari has of time. And this notion lasted hundreds of years. You know, and one guy that picked up on that and who read Aristotle quite well and was somewhat of an expert on Aristotle was this fellow here. And his comes about 600 years later. His name is, well, he's known as Saint Augustine of Hippo. And he was more into religion, but you get the idea with him of where all this went to and how it progressed. He says God is the God of time. He didn't say that, but that's essentially what he meant. He said, look, God is outside of time. He created time, okay? And he says, you made time itself. This is out of his book Confessions, right? Most famous book of Augustine. And he asked the question, he says, what is time? Who can easily and briefly explain it? Who even in thought can comprehend it, even to the pronouncing of a word concerning it? Here this guy reads Aristotle. Aristotle tells it it's number of motion, and here 600 years later, this fellow who read Aristotle quite well, he says, what is time? I still don't know what time is. If no one asks me, I know. If I wish to explain to him who asks, I know not. In other words, he says, we have this intuition of what time is, something flowing, I guess. I don't know, the clock going around, the hands on the clock. He has no notion, he cannot define the word time. And it's interesting that even to this day, you have Stephen Hawking writes a 200-page book, A Brief History of Time. And the only word you won't find defined in there is the word time. You won't find it in the glossary, you won't find it in the body, you won't find it. Hawking never knew what time is, but he called it the fourth dimension. He talks about space-time, time being part of that structure, but he says he doesn't know what he's talking about. That's interesting. It says, neither time past nor future, but the present only really is. There is only a moment of present time. In other words, he's saying there is really no such thing as time, which is, I think, the only thing that he said correctly, okay? He had this notion that, time is just the present. This moment now that just passed, okay, that is time. Not the past, not the future. It's always at the cutting edge between the past and the future. That's the notion that he had, and that's probably the only correct notion that you can have of time. There is no such thing as time. And then he has to justify why, what was God doing before he created time? And his answer is that there was no time before God created time, okay? Before heaven and earth there was no time, why is it asked, what did you then? What did you then? In other words, you meaning God, right? For there was no then when time was not. Okay? So there was no time before God created time. Okay? He moved his magic wand, said, time, let it be. And time became something and started flowing, I guess. Okay? And time began to exist. And that's more or less what relativists have. They call it the Big Bang. They don't call it God. Call it the Big Bang. They say it wasn't set in motion by God. It just is. And it started with the Big Bang. That's when time began. And so you ask them again, what came before that? Well, before that, time did not exist. It was when energy moved, right? Keep this in mind. You have positive energy, according to Stephen Hawking, right? And he was the guru who died 2 years ago, right? You got positive energy, negative energy over here, and they're going to come together. And until that moment, even though you got motion, you don't have time, okay? But it's when negative energy hits positive energy that you start having time. But he reverses the movie, it's the other way around. He's got this thing called energy, and it divides into positive and negative energy, and that's when time begins. That's, I guess, the notion of Big Bang, of somehow energy splitting, and the whole shebang blows up. You figure it out. Try to figure out what energy is in the first place, then you'll make sense out of it. Okay. So what happened from all these people, from the Greeks and Augustine and all the others that came in between? Well, what you have is this group of people, okay? And what's happening here is that you have the Greeks first, and they started very simple. They had 2 dimensions, for example, for a triangle, and that stayed pretty much all the way until the middle of the 19th century, when they started bending the triangles. They put it on a saddle, they put it on a ball, and they ended up with these warped triangles. Okay, they started playing around with the dimensions, or with the lines that formed the triangle. Okay, they started curving them. And towards the end of the century, well, then time became more and more important. It started entering the lexicon of mathematics. People started talking about time, okay? And you ended up, with Einstein saying that time is the fourth dimension. Well, not him, someone else. It was really Minkowski. But it was the fourth dimension. They started incorporating time into their evaluation of location. They said it's no longer length, width, and height, meaning really coordinates. They meant altitude, longitude, and latitude to locate a point. And they said, well, hold it, but that's only the space part. how about the time? That was there at 1 o'clock in the afternoon and at 9 o'clock at night. 9 o'clock at night it was somewhere else. So now they had to incorporate time, and somehow they got carried away with that, lunacy, I call it, and they ended up with 4 dimensions of time. Somehow they equated time to, not dimensions really, to coordinates, but to a mathematicians, like I said the other day, dimension, coordinate, and vectors are all the same thing. Why? Because they're not talking about dimensions, coordinates, or vectors. They're talking about number lines. So when you talk about 4-dimensional space-time, no, it's 4-number-lined space-time. But if they say 4-number-lined space-time, first, you wouldn't know what they're talking about. Second, if you did, you would say, well, that only says that I need 4 numbers to locate a point within space-time. It doesn't mean that space-time is 4-dimensional, because you cannot imagine the 4th 90-degree coordinate dimension or vector to the standard 3. So this is the issue. Time does not run perpendicular to anything. And somehow they did. They said, well, it is, but you can't imagine it. Oh, okay. So you can only approach it from a mathematical, abstract point of view. You cannot try to visualize this from a physical point of view. That's where the problem is. Again, the question is whether mathematics is the language of physics if you cannot even visualize it, if you cannot make sense of it, if you cannot put it on the board. You cannot illustrate the 4-dimension even on film, okay? Because you would have 3 dimensions. Where are you going to put that 4th 90-degree angle, especially on a 2-dimensional screen? So there's no way to illustrate it. And so what they do, they train you to visualize 4-dimensional whatever, tesseracts or hyperspheres or whatever. Okay. By the end of the 19th century, they ended up with this, with time becoming very important. 1895, there on the right, you see it? That's Father Time, okay? And so is the guy on the left, a little more modern version. And he's got the scythe, okay? And that's because Father Time, was related to the harvest time, okay? And so, yeah, now they start talking about time as something a little more important. Becomes popularized, this notion of time, okay? And that's when we begin our brief history of 4-dimensional time, or time as a 4th dimension. And here's a summary, okay? First you have, throughout the 19th century, they believed in the ether. They said there's this ether in the background that forms space itself. Some say that the ether is just a bunch of particles within space. Others say that no, space and ether are equivalent. They're the same thing. Okay, so they have these 2 different notions. And of course they had to explain what light is. And they say, what's the vibration of the ether, of these particles that form the ether, that form space or whatever. And that's the notion all these people have even to this day. Okay, except that nobody wants to say the word ether in mainstream because it's taboo, as one of who was it? One of the Nobel Prizes of physics, mathematical physics, said. Okay. Anyways, the Michelson-Morley experiment in 1887 tried to figure out if there was ether. What they did, they had an interferometer, and here's a version of it so that you can see it. Okay. And they had this interferometer in which they sent a light beam, and they wanted to see if there was a difference in one direction versus another direction of the when the Earth moved through the ether. And they found out that the case on the right, lower right, was not the case. The case was what they verified was the case on the left. In other words, that light had no change in velocity, whether the interferometer pointed one direction or another. Okay, and that's what they expected. With the interferometer, they expected to see light slowing down or retarded with respect to the other beam of light. Okay, and that didn't happen. And so, in general, they concluded, and I'm not sure they concluded because they didn't really, I think, address the issue well enough or left it dangling there. But a lot of people concluded from that, a lot of mathematicians concluded there is no such thing as the ether. And this was a big shock because here they were talking about the ether now since the days of Newton. Even Newton talked about the ether. They were all etherists. And now here comes the Michelson-Morley experiment that says, look, there is no ether. Okay, then now we got to go back to the drawing board and find out, what do you mean there is no ether? So what is light? If light, we always held that light is the movement of the ether, the vibration of the ether, and now you're telling me there's no ether? Then now we're back to square one. What is light? Okay? And yeah, they talked about waves, but then the waves of what? What is waving? And so this was an important issue. And one of the fellows who addressed it was this fellow here. I'll put this back up here. His name is George Fitzgerald. He was Irishman. Okay, and he says, he theorizes. Here comes where the weirdness starts coming into the, you could call it physics. It's really not physics, the mathematical physics world. He says, theorizes that moving objects shorten in the direction of their motion, what is known as length contraction. A lot of people say, oh, Einstein invented all that. No. It came from Fitzgerald when Einstein was almost not even born. Einstein was only 10 years old in 1889. So I don't think Einstein came up with length contraction. Neither did he come up with time dilation. This came from these guys, okay? This was before Einstein was even born almost. And George Fitzgerald said, well, the reason the Michelson-Morley did not detect the ether is because the interferometer, the arm, shortened in the direction of travel. It squeezed. It became shorter. We have length contraction of the interferometer, and that explains the difference of why light arrived at the same time, you know, from the two mirrors. That was his solution. And a lot of people laughed at him. A lot of mathematicians in those days laughed at him, but Hendrik Lorentz, who was a big guy in those days, you know, he was like the Einstein, the Stephen Hawking of those days. And Hendrik Lorentz said, I'm going to tackle this problem. And he went in there and he developed the mathematics for it. And he says, he concludes essentially, observers measure the same speed of light, but arrive at different measurements regarding when events happen. Okay, and so he's going to apply this to both length contraction and to the speed of light. Okay, and he's going to introduce the observer. Okay, and that's where we start running into trouble. Here it is. This is his notion with respect to length contraction. Lorentz develops the Lorentz factor. Okay, which is that little equation up there, and it's not that difficult to understand, okay? What he's saying is, you see velocity squared, v squared? Well, when velocity squared approaches the speed of light, little c squared, in other words, velocity of light, 300,000 kilometers per second, right? If the velocity of the object is, I don't know, 280,000 kilometers per second, 290, 275, whatever number close to the speed of light, well, you have almost one, just a number slightly less than one. Okay, and so if you have 1 minus a number that is slightly less than 1, you end up with a very small number. Okay, and so what happens, he's got a very small number, he takes the square root of that, and that's a smaller number, he multiplies it times the length of the object, the real length or the proper length of the object, and when you multiply that small number, fraction, right, times the length of the object, you end up with the length contraction. The contraction that an observer in motion is going to see. Okay, that's essentially what it is. It's not too difficult. Just put some numbers in there and you'll figure it out. It's not that difficult to figure out. Okay, and he applies this also to time. Okay, and that's where we start running into trouble. Okay, because he says, look, if you apply my equation, my factor, and you apply it to time, you get the same thing. You got a stationary observer who measures time in one way, but then you have the moving observer, okay? And he's going to measure time a different way, and he's also going to do this little fancy mathematical calculation, and he says, okay, time dilates. Time is what shortens. Time is what squeezes, okay, or lengthens, depending on the speed in which you're traveling. So time is not time for everyone, as Newton thought it was a universal time. Aristotle also says that. I should have brought the reference, but if you read physics, you'll find that time is, according to him, time is universal. These guys are saying, no, it depends on the observer. Okay? That's when we get to a little bit of trouble, because now we're relying on observers. That's why in rational physics we say there are no observers in science, because they keep introducing the observer and telling you they're relying on this witness, on his testimony. They're telling you what the witness perceived or measured. And you say, well, this guy measured something different than that one over there, because this guy was in motion, this one was standing still with respect to a reference frame, right? And so, no, we don't deal with all that nonsense, okay? And here, let me put it in a little picture. I think I got it here. Yeah. Give me a second here. Okay, here it is. You have Einstein and Lorentz. Lorentz is on the little train there, on a little cart that's moving. Okay, here it starts. Okay, Lorentz sees this. Einstein sees this. He sees that the light coming from Lorentz hits the two detectors at the same time. Lorentz, on the other hand, he sees one hitting one detector first, then the other. Okay, why? Because he's moving. And so the light from the event comes to his eyes at different times because he's in motion. Here it is again. Einstein sees them both hit at the same time, the light cone, whereas Lorentz sees the light cone hit one detector before it hits the other. Why? Because he's in motion. That's essentially what they're saying. So what's wrong with this picture? Well, what's wrong with the picture is obvious. We don't care about observers. Let's kill both observers. Let's kill Lorentz and let's kill Einstein. Let's get rid of both of these guys. Did light hit the two? If we have two detectors there, light detectors, will the detectors detect it at the same time or not? That's the only issue. And if they detect it at the same time, they happen simultaneously. If they detect it at different times, they didn't happen simultaneously. We don't need an observer. All we need is objectively to put two sensors there to detect whether light hit them at the same time or not. That's it. We don't need their testimony. These guys are saying, look, mathematically we can show that the guy moving visualizes, observes, measures, detects something different than the guy who's stationary. That was their notion. This is what they had in their minds. And that's what we have today. We have, mathematics has developed around the observer. That's why we don't like the observer. We don't like testimony. We don't like witnesses. In science, the first thing we do is what the mafia does. We wipe out the witness. Forget about the witness. And these people are relying on, they're telling you mathematically what one witness will see and what another one will see. And then they compare and they say, well, see, for this guy, time only 1 second went by, but for this guy, it went 2 seconds went by. That's what they're telling you. And we don't care. I mean, two events happened at the same time or not. Either the asteroid hit the moon at the same time that the moon hit the asteroid. You can't say, well, the moon saw something different than the asteroid, because the moon was more or less stationary and the asteroid was moving. It's all idiocy, what mathematical physics has created with this monster called time. Okay, so how do we do it in rational science? Well, in rational science, the first thing we do is define terms so that we can use them consistently, rationally, scientifically. Okay, here it is. Okay, we start with the definitions that Mr. Aristotle bungled. Okay, you can forgive him because he was the first guy to attempt it. Okay, we can say that poor old Ari, he didn't know any better, but after 2,000 years, nobody made any improvement. We don't have definitions for these words, so we have to define them. Motion, two or more locations of an object. Okay, we're done. If it has two locations, what is a location? Set of distances to every object in the universe. So now you can talk about motion in terms of universal time frame or space frame, matter frame, okay? Comparison of two motions, okay? Time is a comparison of two motions. And the difference especially is you move by definition. Time requires a memory, a recording device. You need memory. You can't do time without memory. And it's interesting that Aristotle mentioned that as well. And again, I should have pulled out that reference. I'll pull it out next time for sure. Okay, but yeah, he mentions that in order to have time, you need to have some kind of you got to memorize something. And yes, you can't do time without memory. Okay. Okay, and here's a pictorial representation of that. Motion, two or more locations. We have a box on the top, and let's assume that the little balls there, dots, let's assume God moved his magic wand and made them stand still, completely still. Motion just means that the box is changing its distance with respect to each one of those dots. Okay, that's all it is. Time, on the other hand, requires two objects. We're going to introduce a cylinder now, and we're going to compare the motion of the cylinder versus the motion of the box. Okay, that's what we're going to be comparing. And you're going to need memory because you're going to need to memorize the previous locations in order to have this sense of time. Okay, otherwise you don't have time. Otherwise you just have motion. Now you can have time also in the first film there, and the one about motion, only if you compare the box against its original point, its starting point. Then you can, if you memorize that location, then yes, you can have motion of a single object, but essentially what you're doing is comparing the motion of the last frames of the film versus the first frames of the film. Okay, so keep that in mind. That's the context here. Okay, so here we have, hold it, where am I? There it is. Here's a, you say, well, what is time? What notion do we have now? Where did I get this notion, in fact, you might ask, okay? And here is what we typically associate with time: seconds, minutes, hours, days, years, right? 60 seconds in 1 minute, 3,600 seconds in 1 hour, 60 minutes, right? 86,000 seconds in a day, 31 million in a year. Okay, that's the number of seconds. What is a second? Well, a second is 30 kilometers. That's what a second is. It's the distance the Earth travels in 1 second, 30 kilometers approximately, right? We came up with this by dividing the year. We divided the year into days, then into hours, minutes, seconds. That's how we came up with all this in retrospect, okay? And so we had a certain distance. We said, okay, we had 1 year here. It took 365 days and nights, right? So that was the starting point. In fact, the definition of the word year has not changed. We still say that a year is one orbit of the Earth around the sun. That's a year. It's not measured with atomic clocks. No, we don't measure years in atomic clocks, with atomic clocks. No, we measure it by how many rotations the Earth made around the sun. So if you want to know how many candles you have on your birthday cake, you don't bring an atomic clock to your birthday party. No, you count how many times the Earth went around the sun. That's how we measure that, okay? That's the definition. That's still the formal definition of year, okay? And 1 second of motion on the hand of the clock, right? The second, when it moves 1 second, the Earth moves 30 kilometers, except for flat earthers, okay? The Earth doesn't move there. It's the sun and the moon that move around the top, I guess the heavens. Okay, but for normal people, rational people, yeah, it's the Earth goes 365 days to go around the sun, okay? Globe, okay? It's a spherical Earth going around a spherical sun, okay? Let's make sure we get that right. and when it travels 30 kilometers, you got 1 second. That's what the second hand on the clock, okay, moved 1 second. Okay, and here it is, just so that you can see why it's time is a comparison to motion. If I can get this thing here, okay, here it is. Let's see if I can get it. Here's a pictorial representation of that. Okay, the Earth moves around the sun, round Earth, okay, spherical Earth, and the clock on the right moves 1 second. Obviously, it's moving. Both of them are moving quite fast. But what we're doing when we're saying 1 second, we're comparing the second hand on the clock moving one little notch, and the Earth moved 30 kilometers. So we're comparing the two motions. We're comparing the motion of the second hand against the motion of the Earth around the sun. That's what time is, comparison of two motions. So if you ever wanted to know what a second is, now you know. A second is 30 kilometers. That's what a second is. With that, I'll see you, on Sunday? And for those of you who are interested, I'm starting the Spanish, I've already had the channel, but I'm starting up the channel on, I think it's going to be Friday, a couple days. I was waiting to translate the book into Spanish. Now I did. I uploaded it for those who are interested. You can find it also at ropehypothesis.com. And I also was translating a couple articles, Extinction articles, which is so pertinent today, right? We may be headed towards extinction relatively soon. Soon in geological terms, right? Anyways, so I was waiting to translate that as well as the book. Now I have done that, and so I'm going to be uploading those on the articles on Friday, and that's when I start my channel, which is an attack above all, first against the flat earthers. Yeah, that's true, because they made a couple videos last year on me. In August, I was going to answer, but I just got sick, and then I decided to write the book, and then I translated and a lot of stuff in between, including the coronavirus and all that. But now it's translated. I have uploaded the book. I'm going to be uploading the two articles, 3 articles really, 2 published and 1 informal, and that's when I start crank up my Spanish channel. So for those of you who are interested, remember there's always, YouTube has this automatic translation, so it's not going to be perfect. I talk in Argentine Spanish. Not even the Mexicans understand us. So I'm going to start that up on, I think, Friday, and if you're interested, you can tune in. Okay, so we'll see you then. Bye-bye.